Hello everyone and welcome to Vibrations and Acoustics. We're going to do a second method for solving this problem. If you saw my previous video of method 1 of a spring mass system, finding the response of a spring mass system, then you can go ahead and look at that for the quicker way of doing it. But I'm going to go through here and kind of painstakingly show the details and back up any assumptions that we've done on this kind of problem before, unlike the other one. So if you can go ahead and write down these values, I'm just going to go ahead and skip right into the problem, so I'm going to have to take this away. Okay. So when you're looking at this problem, I'm going to go ahead and draw the free body diagram. You've got a block right here, and we're going to measure x in this direction, basically. So that even though there's an angle of theta, we don't really care about it that much. But in this direction, okay, so we have a kx right here. We have f of t, the forcing function, f of t right here. And then we also have mg right here. But that will translate into a force this direction of mg sine of theta, because you're sitting at an angle of theta right here. Okay, so that's our basic setup right here. So you can basically just look at it like that and ignore the mg. And then you've got a horizontal system, basically, with just another force added into it. Okay, so in setting this up, we first need to find the equation of motion. And to do that, we're going to use the sum of the forces, which is going to equal mx double dot, which is always the result of the sum of the forces. You always have a mass times an acceleration when you have a sum of the forces, is equal to mg sine of theta, this force right here, plus f of t, because we're assuming positive is this direction, minus kx. Okay, and now in order to get the equation of motion from that, all you have to do is go mx double dot plus kx minus mg sine of theta. So now you have your mass and your spring constant, and if for some reason we had a damper in here, that would also come into this equation. And then you have the initial starting location, basically, is what this is going to give us, which is then equal to f of t, which is the forcing function. Okay, so at static equilibrium, basically you set this block up on the ramp and hook it up to the spring, and then just kind of let it sit, let it settle to wherever it is. Equilib. I'm going to abbreviate that. What you have to do is find x static is equal to mg all over k sine of theta. Now this came from this equation if you assume f of t is non-existent. So basically, in order to get static equilibrium, you assume f of t is equal to 0. So you just have this equation and you assume that there's no motion of any kind. So x can't be accelerating. You're just solving for the x static position. So there's no motion, so f of t is gone, and any acceleration x is gone. And then you set that equal to 0, and you solve for x. And this will give you x static. So looking at this, we have 100 times 9.81 all over 4,000 newtons per meter times sine of 20 degrees, which is the theta, which is equal to 0.084 meters. Okay, so this is x static, and like I said, it's just if you set up the block on the ramp and let it go and let it kind of settle to wherever it is. That's x static. And we're going to save this for the final response, because if you're looking for the total response of the system, you want to know what the response of the system is from the spring being not compressed or extended at all to being compressed and extended, and that means this has to be included. Okay, so now we're going to define x tilde, which is equal to x minus x static. Now x tilde, as you can see from this equation, is a standard response of the system, x naught basically, minus the initial x static position. So wherever this x tilde is, wherever this block is, minus the displacement, wherever this block is due to the forcing function, minus this displacement that's there just because of where the block sits when it's just sitting still. So that's how that's defined. So this is from the weight, static. So then we want to actually find x, because we want to know what the total response from the forcing function is. And you could solve for just x tilde, and that would be a little bit simpler, but if again we're looking for total response, so you have to find the response of the total response right here, and then which will include the static function basically. So then x of t or x is equal to x tilde plus mg all over k sine of theta, which is just this calculation up here, which is equal to x tilde plus 0.084 meters. So you're putting in the static equilibrium to whatever just the forcing function result is, which will give you the total result. I think I may have stated that incorrectly earlier. This is the entire displacement of the system, and then if you subtract the static displacement of it, then you get the displacement just due to the forcing function. So this x tilde is just the displacement due to the forcing function. So now, if you're looking to solve this problem and you want to find the displacement, you have to go x tilde of t is equal to x tilde, the homogeneous solution of x tilde of t, plus the particular solution of x tilde of t. Okay, since we know it's a vibratory system, we don't have to solve out, do a bunch of differential equations or derivatives or calculus to find the homogeneous and the particular solution. Since we know it's a vibratory system, we can just go x tilde t p of t is equal to x sine of 6t, which is the new amplitude, but the omega has to match the omega of the forcing function that was given in the problem, which is, I'll just write it up here, f of t is equal to 100 sine of 6t, where this is f naught, forcing amplitude basically, and this is omega. So the omega has to match in the particular solution, because the particular solution has to see the form of sine of omega t, basically right here. And then, let's see here, make sure I get this correctly. Once you have xp of t, you can basically substitute it back in to our equation of motion up here, and you'll be able to solve for the x, basically, this value of x. So if you go ahead and do that, and you substitute x sine of 6t back up here into the equation of motion, and you replace these x's with x tildes, and since we're working with x tilde, you no longer have this. I'll just write it out. So mx tilde double dot plus k x tilde is equal to f of t, x tilde, just x tilde, sorry. It's not a damper, it's a spring. Since we're working with x tilde, which is x minus the x static, you don't have to include this function, which is basically this piece right here. So that's basically what that is. Once you find x static, you can eliminate the weight values from any of your equations of motion. Okay, so then solving this out, you get minus mx omega squared sine of omega t plus k x, this should be large x, I apologize, sine of omega t, where we just substituted this right in there, is equal to f naught sine of omega t. Now you'll notice I'm doing this symbolically. If you wanted to substitute numbers in here, that's fine, but what we're going to do here is cancel a whole bunch of this stuff, so it's really not necessary, because you can factor out a sine of omega t just like that, and you will end up with, and if you solve this out, this is equal to f naught now, and if you solve this out for x, x will equal f naught all over k minus m omega squared. And if you look at that, f naught is equal to 100 from up here, which is then equal to 100 newtons all over 4,000 newtons per meter minus, I'm not going to put in all these units, 100 times 6 radians per second. I guess I just did put all those units in there. Sorry. Squared, which is going to equal 1/4 meter, 1/4 meter, which is equal to our leading value of x. So 0.25. The large value of x, the amplitude of the particular solution, is going to be x. So now we need the homogeneous solution. So xh, h of t, that's an h. Again, in a typical vibratory system, we know that sine of omega nt plus phi is equal to a sine of omega t plus phi. And we know that omega n is equal to the square root of k over m, which were values given in the problem. So we got 4,000 all over m, or at 100, which is the value of m. Take the square root of that, and you get 6.325 radians per second, which is our omega n. And okay, you can solve for a couple different ways, but what I'm going to do is just go ahead and go straight into initial conditions here, because we know that our x tilde of t is equal to a sine of omega nt plus phi plus x sine of omega t. Now we have x, we have omega n. We need to solve for this a and this phi here in the homogeneous part of it. We're able to assume these. You just have to remember these equations, so hopefully you don't have to solve a differential equation every time you do one of these problems. But in order to do this, we're going to go ahead and use the initial conditions that were given, which are zeros. So the x displacement is 0 and the x velocity is 0. So if you're looking at x naught tilde, which is the original displacement, you've got x naught minus xst. Well, we know that x naught, the original displacement of the entire system, is equal to 0, because our initial conditions are 0. So basically, saying your initial conditions are here and you're trying to find the entire response of the system, you're saying, okay, I'm going to set this block, I'm going to push it up the hill so that you don't extend the spring and the spring exerts no force on the block, and then I'll release the block from that position. It'll fall in equilibrium, and then I'll start the forcing function. You have to start from where you let go of the block and let it fall into the static spot. So from there, we're saying that is equal to x. And we know x static is 0.084 from up here. So then x tilde naught, which is the total response minus the static equilibrium distance, is going to equal negative 0.084 meters. Okay. So now, and then we know that x tilde dot, well, just taking the derivative here of a constant, then you're going to end up with 0. Okay then, so that's got us all set up right there. Now, we have x tilde and x tilde dot. X tilde dot, from our earlier equations again, the stuff that we did up here with the x particular and so on and so forth, we know that x tilde dot is equal to a sine of phi, which is equal to negative 0.084, or x tilde, I'm sorry, I apologize for that. But that's the standard amplitude sinusoidal motion with the phase shift of phi. Let me bring this down here so you guys can see all the past stuff that we did. We also know that 0, which is x tilde dot, this is equal to x tilde original, and we'll say this is x tilde dot original is equal to 0, which is equal to a omega n cosine of phi plus x omega, which is just the derivative of this equation up here. So the x tilde displacement, the original displacement, is just a sine phi. Fair enough. So now if you set these two, if you solve for these two, stick them together, then you go a cosine of phi is equal to negative x omega all over omega n minus, let's see here, make sure I got this right. Okay, yeah, 1/4. Let me make sure. Nope. Sorry, that's not correct. This is equal to. This is a negative. Sorry. So yes, taking this equation, you take a cosine, you divide by x, subtract this over to the other side, divide by omega n, then you have a cosine phi, which will basically be a variation of this. You solve for that, you get negative x omega over omega n, which is going to equal 1/4 meters, which we calculated earlier, which is x, the value of x, the large value of x. This is capital X. because this is this x up here. Okay, and then 1/4 times 6 radians per second all over 2, I can't read the value here, omega n 2.3, or no, omega n is 6 point, sorry, the notes on this are a little messed up, 6.325 radians per second, which is then going to yield negative 0.237 meters, which is equal to a cosine phi. So then A is equal to the square root of negative 0.084 meters squared plus negative 0.237 meters squared, which is equal to 0.251. And then I'm going to go ahead and solve for phi here, and then I'll explain where this equation comes from a little bit, and how you don't really have to do this whole solution up here, because this is a little bit excessive. And if you watch my method 1, I don't do all this work. It's quite a bit easier. A tan of negative 0.084 all over negative 0.237, which is equal to 0.3406 radians. And this is meters. So you have your A and you have your phi now. And the reason we need these is because up here solving for x tilde, we have a sine of this. So we were solving for this A, we had this omega, we solved for this phi, and we solved for this x. But we didn't solve for this x was solved up here. Okay, so now I'm going to go ahead and show you where these equations come from. When you have an undamped system, which means just a spring and a mass, A is going to equal the square root of x naught squared plus x naught dot all over omega n minus omega over omega n times f naught all over k. This f naught is the small f naught, which is from the forcing function, is 1 over 1 minus omega over omega n squared. And omega over omega n is equal to r, if you've ever seen that kind of notation. So this is the amplitude A. Phi is equal to A tan 2 of x naught by, this is MATLAB notation, so this is the inverse tangent of x naught divided by, the comma is basically divided by, x naught dot divided by omega n minus omega over omega n f naught over k of 1 over 1 minus omega over omega n squared. And that's how you solve for phi. And then you know that x of naught, again for an undamped system of initial conditions equal to 0, x naught is equal to a sine of phi, and x dot of naught is equal to a omega n cosine of phi plus x omega, which we derived up here basically just by taking these derivatives, but that's where this equation came from. So for an undamped system, you can basically just jump to this set of equations. And then you know that x dot of 0 is then equal to a omega n cosine of phi plus f naught omega over k all over 1 minus omega over omega n squared. So this jumps right to here just by solving this out a little bit more and changing x omega, this large x, which we solved for. We solved for this large x up here, which is f naught over k over omega, which translates directly into this. So basically, if you have an undamped system with a set of springs, you can jump right to these equations. But if you want to do everything from scratch, you can derive the equation of motion and go through all these other steps. So then, in solving for these values, your final solution is going to be x of t, total final solution, is equal to 0.251 sine of 6.325 t plus 0.3406 plus, which is the homogeneous solution, just putting in a omega n and phi, 0.25 sine of 6t, and then technically this equation as it sits right now would only be x tilde. This is the displacement of the block from the equilibrium position. But if you want to find the total response of the system, including that caused by the equilibrium weight basically, then you add in x static, which is 0.084. Yep. 0.084. And that's going to be in meters, and that is x of t. So that is your final answer. So in method 1, I basically jump to these equations and solve it out a little bit quicker, and I explain it a little bit. But in method 2 here, this will get you through a test, and you can derive every single thing you need in order to finish the test. Or you can just jump to these equations for an UMDANT system, and if you have an equation sheet, do this method.